Let's talk a little bit about activation energy, which came up in the previous video, but now I want to go into a little more detail about exactly how activation energy can affect a chemical reaction. Okay, and so if you remember in the last video, I showed you the Arrhenius equation, which described this rate constant K as a function of things like a pre-exponential factor and activation energy. So now let's say that I do this reaction, same reaction, but twice. Okay, once at a certain temperature T1 and another time at a certain temperature T2. Because the temperature is different, the rate of the reaction is also going to be different. And I can use this Arrhenius equation to figure out what the relative rates are going to be at these different temperatures. Okay, so let me show you what the formula looks like in that situation. Okay, Arrhenius equation says that the natural log of the quantity K2 over K1 is equal to minus activation energy over R is 1 over T2 minus 1 over T1. So if I use this formula, I have to make sure that I use the right units. R is going to be 8.314 joules per mole Kelvin. Activation energy typically is in kilojoules per mole. So make sure you convert, right, multiply by 1,000 to go from kilojoules to joules. Okay, the point is that this activation energy represents a barrier, right? It's the amount of energy that I need to overcome for this reaction to take place. So you can see this on the graph on the right-hand side. Okay, here, let's say, are two reactants, A and B, and here are two products, C and D. Even if the products have a lower energy than the reactants do, that doesn't mean that I can go straight from A and B to C plus D. I actually have to go up and then back down, okay? Because I have to overcome things like electron clouds and repulsions when I'm bringing these molecules closer together. So the amount of energy that I need to overcome this unfavorable repulsion in order to eventually get the payoff of the more stable products is called the activation energy, EA. Okay, and so different chemical reactions are going to have different activation energies. And so the point is that I have a Boltzmann distribution here showing that there are different molecules with different kinetic energies, right? There's an average kinetic energy, but that's just the average. It doesn't mean that every single molecule has exactly the same kinetic energy. Some might have more, some might have less, okay? If I have, let's say, an activation energy over here, then this piece represents all of the molecules that have enough energy to overcome the activation energy and actually react. The higher I make the activation energy, the smaller the fraction becomes. That's why the rate goes down. Similarly, at a higher temperature, okay, the shape of the curve changes. And so I can get more and more and more molecules with a higher fraction reacting and overcoming the activation energy at a higher temperature compared to a lower temperature, which also makes sense because at a higher temperature, the molecules have a higher average kinetic energy. Higher average kinetic energy means that they're moving around more, they can collide more, and maybe they can collide more effectively, and therefore increase the rate of this chemical reaction.